Hello and welcome to part 2 of lesson number 2 in Unit 6, solving problems with quadratics in our grade 10 academic math class. So we've tackled one example already of an optimization problem. We're going to look at a variation on it, but the same idea in example 2. So example 2 reads, the perimeter of a rectangle is 400 meters. What are the dimensions if the area is a maximum? So again, if you want to pause the video here and write out the let statements, that will be really helpful. I'm just going to cruise right over them, so it would certainly be important to have them down before we start working the problem. Okay, so we read this. We're asking ourselves what kind of question this is. Well, we see the word maximum. And the word maximum, when we see it, that's talking about a quadratic. It's talking about a maximum value, which means a vertex. So we are able to identify this as an optimization problem by the use of the word maximum. Also, area, the word area in there, is also an indication that we're going to be dealing with a quadratic. Since, without spoiling too much of what's going to be coming, we're also going to be solving quadratic equations that are not optimization questions. We're actually going to be solving them. So there's going to be two types of word problems that we look at that involve quadratics. The first, our lesson today, optimization. So once we've identified our let statement, so we have P for perimeter, L for length, W for width, all in meters, and then we let capital A represent area in square meters. Obviously, it's important to get our units on there. Now we're going to build some equations. So let's start with equation number 1. The first sentence that we read here says, the perimeter of a rectangle is 400 meters. So let's start by just writing out sort of a general perimeter. So the perimeter of a rectangle will be equal to 2 lengths plus 2 widths. And we happen to know that the perimeter is 400. So in this case, we can continue on with 1, and we're going to call that 400 equals 2 lengths plus 2 widths. Okay, there's our first equation. Second equation is kind of hidden in there because it says, what are the dimensions if the area is going to be a maximum? So for us, our second equation is actually going to be an area equation, where area of a rectangle will be equal to length times width. So there are our two equations. Same as last time, in order for us to optimize this, we need to actually eliminate one of these variables. So let's have a quick look down the line. As I said last time, we need to be able to identify which of these equations is linear and which of them is quadratic. And we do that by identifying degree. So if we look at this equation here, this 400 equals 2L plus 2W, this is a degree 1 equation, in that the variables have as their largest exponents a 1. But if we head down here to our area equation, what's interesting is that yes, the exponent on L is 1 and the exponent on W is 1, but combined this makes a degree 2 function. So this is our quadratic. As before, we are going to substitute our linear into our quadratic. So in order to do that, I'm going to do a little bit of rearranging here. I'm going to rearrange number 1 to isolate one of our variables. So I'm going to just do L, I guess. So 2L will be equal to 400 minus 2W. And now I'm going to divide both sides by 2, which is going to give me L is equal to 200 minus W. And that's what we're going to call 3, an isolated L. Now some people, their temptation is to leave it right here. We need to have an isolated variable. So not 2 L's, we want 1 L. So we need to continue on to isolate that variable. This would have worked equally well with W. It doesn't matter which one you picked. I just picked L because it was first. Okay, so now we are going to substitute 3 into 2. Substitute 3, which is our rearranged number 1, our linear equation, into 2, which is our quadratic. So we have area is equal to, now in the place of length, we have 200 minus W, and the width, of course, still remains just W, kind of hanging around there. So we're going to expand this thing out. We are going to multiply each of these two terms by W, so that's going to give us area equal to 200W minus W squared. So this is a quadratic. Let's rearrange it a little bit so that we can get all the terms in the proper order. So a is going to equal minus w squared plus 200w. So there's no c value. That's okay. I'm just going to take a look at my spacing here. Yeah, spacing looks all right. So I'm going to, now that I have my quadratic, I'm going to go after that maximum value. I think it was a maximum. Yep, we're after a maximum value here. So we're going to, as before, complete the square. So I'm going to, maybe I'll make a new column for that. Complete the square. And let's take our quadratic. That was going to be a equals minus w squared plus 200w. We're going to start by common factoring out our a value. So our a value here is -1. We need to start building our perfect square trinomial with a perfect square. So area will be equal to minus, and then we've got w squared minus 200w. And we don't have any constant this time to leave behind, so let's just start building. We need to add something, and we need to subtract something. And that is going to give us our perfect square trinomial and the thing to balance it. So how do we go about doing that? Well, we take half of our b value, so half of -200 is 100, and we have 100 squared. That's going to give us 10,000. So I did not leave enough space in there. I'm going to rewrite that. So we need 10,000, I'm sorry. 10,000, and we subtract 10,000, and there we go. So again, I know I say this all the time, this plus 10,000 was put in to create our perfect square trinomial. This value was put in to balance the equation. So let's free that -10,000 from our bracket by multiplying it by -1. Get it out of there, times -1, and let's see what our next line looks like here. So we have a equal to negative w squared minus 200w plus 10,000, and -1 times -10,000 is plus 10,000. All right, and now we factor. A equals negative, and here we know we're going to have a w in there. We know that our value in the brackets will be negative, and that value will be what multiplies to positive 10,000 but adds to -200. That will be 100, and there's our plus 10,000 hanging around outside our bracket. Okay, so let's interpret our vertex here, because our vertex is 100 and then 10,000. So again, these variables that we've been using, in theory, would sort of correspond to like input and output, or x's and y's. So our input value is 100, which is the width of this rectangle that we're building, and the y, which is our area, our maximum area in this case, is going to be 10,000 square meters. That's how we interpret the vertex, the information there. We still, however, need to go and figure out what our length is. So we are going to go get our length. So we are going to find L. And the way that we are going to find L is subbing into that original equation. So we had L was equal to 200 minus W. That's going to be 200 minus 100, and that gives us 100 meters. So we want to write ourselves a therefore statement. So therefore, the dimensions that give maximum area are 100 meters by 100 meters. And there is a little tidy therefore statement to sum it all up. Again, I'm just going to zoom out. We're just going to recap what we did here. So we read through our question. We found our clue word maximum, which means that we're going after a quadratic, and specifically the vertex of a quadratic. We saw that this was an area question, so we know that we're going to need an area formula in there somewhere, or an area equation. We create the two equations, the linear and quadratic equations, based on information in the question. We substitute the linear into the quadratic, always, always, always linear into quadratic. Then we complete the square once we have our expanded out quadratic and standard form. Complete the square, interpret our vertex, find the other variable, which in this case was L, and then write ourselves a nice little therefore statement. So that's example number 2. This would be like the area subset of optimization questions. Come on back to part 3. We'll finish this lesson up, and then you can go and try some homework. Exciting!